the denominator is pretty expensive. And that's because you have to iterate over every word in the vocabulary and work out about what this is. But actually doing the skip-gram model with negative sampling is the part of homework too. So you'll get to know this model well. So the point is that if you use this naive softmax, even though people commonly do use this naive softmax in various neural net models, that working out the denominator is pretty expensive. And that's because you have to iterate over every word in the vocabulary and work out these dot products. So if you have 100,000 word vocabulary, you have to do 100,000 dot products to work out the denominator, and that seems a little bit of a shame. And so instead of that, the idea of negative sampling is where instead of using this softmax, we're going to train binary logistic regression models for both the true pair of center word and the context word versus noise pairs where we keep the true center word and we just randomly sample words from the vocabulary. So as presented in the paper, the idea is like this. So overall, what we want to optimize is still an average of the loss for each particular center word. But for when we're working out the loss for each particular center word, we're going to work out the loss for each particular center word and each particular window. We're going to take the dot product as before of the center word and the outside word, and that's sort of the main quantity. But now instead of using that inside the softmax, we're going to put it through the logistic function, which is sometimes also, or often also called the sigmoid function. The name logistic is more precise, so that's this function here. So the logistic function is a handy function that will map any real number to a probability between 0 and 1 open interval. So basically, if the dot product is large, the logistic of the dot product will be virtually 1. Okay, so we want this to be large, and then what we'd like is, on average, we'd like the dot product between the center word and words that we just chose randomly, i.e. they most likely didn't actually occur in the context of the center word, to be small. And there's just one little trick of how this is done, which is this sigmoid function is symmetric. And so if we want this probability to be small, we can take the negative of the dot product. So we're wanting it to be over here, that the dot product of a random word and the center word is a negative number. And so then we're going to take the negation of that. And then again, once we put that through the sigmoid, we'd like a big number. Okay, so the way they're presenting things, they're actually maximizing this quantity. But if I go back to making it a bit more similar to the way we had written things, we had worked with minimizing the negative log likelihood. So it looks like this. So we're taking the negative log likelihood of the sigmoid of the dot product. Again, negative log likelihood, we're using the same negated dot product through the sigmoid. And then we're going to work out this quantity for a handful of random words. We key negative samples, and how likely they are to sample a word depends on their probability. And this loss function is going to be minimized, given this negation, by making these dot products large and these dot products small, means negative. So there's just then one other trick that they use. Actually, there's more than one other trick that's used in the Word2Vec paper to get it to perform well, but I'll only mention one of their other tricks here. When they sample the words, they don't simply just sample the words based on their probability of occurrence in the corpus or uniformly. What they do is they start with what we call the unigram distribution of words. So that is how often words actually occur in our big corpus. So if you have a billion word corpus and a particular word occurred 90 times in it, you're taking 90 divided by a billion, and so that's the unigram probability of the word. But what they then do is that they take that to the 3/4 power. And the effect of that 3/4 power, which is then renormalized to make a probability distribution with z, kind of like we saw last time with the softmax, by taking the 3/4 power, that has the effect of dampening the difference between common and rare words, so that less frequent words are sampled somewhat more often, but still not nearly as much as they would be if you just use something like a uniform distribution over the vocabulary. Okay, so that's basically everything to say about the basics of how we have this very simple neural network algorithm, Word2Vec, and how we can train it and learn word vectors. So for the next bit, what I want to do is step back a bit and say, well, here's an algorithm that I've shown you that works great. What else could we have done, and what can we say about that? And the first thing that you might think about is, well, here's this funny iterative algorithm to give you word vectors. If we have a lot of words in a corpus, it seems like a more obvious thing that we could do is just look at the counts of how words occur with each other and build a matrix of counts. Co-occurrence matrix. So here's the idea of a co-occurrence matrix. So I've got a teeny little corpus. I like deep learning. I like NLP. I enjoy flying. And I can define a window size. I made my window simply size 1 to make it easy to fill in my matrix. Symmetric, just like our Word2Vec algorithm. And so then the counts in these cells are simply how often things that co-occur in the window of size 1. So I like occurs twice, so we get 2s in these cells because it's symmetric. Deep learning occurs 1, so we get 1 here, and lots of other things occur 0. So we can build up a co-occurrence matrix like this, and well, these actually give us a representation of words as co-occurrence vectors. So I can take the word I with either a row or a column vector since it's symmetric and say, okay, my representation of the word I is this row vector. And that is a representation of the word I, and I think you can maybe convince yourself that to the extent that words have similar meaning and usage, you'd sort of expect them to have somewhat similar vectors, right? So if I had the word you as well in a larger corpus, you might expect I and you to have similar vectors. because I like, you like, I enjoy, you enjoy, you'd see the same kinds of possibilities.
Hey, Chris, could you answer some questions?
Sure.
All right, so we got some questions from the negative sampling slides. In particular, can you give some intuition for negative sampling? What is the negative sampling doing? And why do we only take one positive example? Those are two questions that could be answered in tandem.
Okay, that's a good question. Okay, I'll try and give more intuition. So is to work out something like what the softmax did in a much more efficient way. So in the softmax, well, you wanted to give high probability to in predicting a context word that actually did appear with the center word. And well, the way you do that is by having the dot product between those two words be as big as possible. And part of how, but you're going to be it's more than that, because in the denominator, you're also working out the dot product with every other word in the vocabulary. So as well as wanting the dot product with the actual word that you see in the context to be big, you maximize your likelihood by making the dot products of other words that weren't in the context smaller, because that's shrinking your denominator, and therefore you've got a bigger number coming out and you're maximizing the loss. So even for the softmax, the general thing that you want to do to maximize it is have dot product with words actually in the context big, dot product with words not in the context be small to the extent possible. And obviously you have to average this as best you can over all kinds of different contexts, because sometimes different words appear in different contexts, obviously. So the negative sampling is a way of therefore trying to maximize the same objective. Now, you only have one positive term because you're actually wanting to use the actual data. So you're not wanting to invent data. So for working out the entire J, we do work this quantity out for every center word and every context word. So, we are iterating over the different words in the context window, and then we're moving through positions in the corpus. So we're doing different VCs. So, gradually we do this. But for one particular center word and one particular context word, we only have one real piece of data that's positive. So that's all we use, because we don't know what other words should be counted as positive words. Now, for the negative words, you could just sample one negative word and that would probably work. But if you want a slightly better, more stable sense of, okay, we'd like to, in general, have other words have low probability, it seems like you might be able to get better, more stable results if you instead say, let's have 10 or 15 sample negative words. And indeed, that's been found to be true. And for the negative words, well, it's easy to sample any number of random words you want. And at that point, it's kind of a probabilistic argument. The words that you're sampling might not be actually bad words to appear in the context. They might actually be other words that are in the context, but 99.9% of the time, they will be unlikely words to occur in the context, and so they're good ones to use. And yes, you only sample 10 or 15 of them, but that's enough to make progress, because the center word is going to turn up on other occasions, and when it does, you'll sample different words over here so that you gradually sample different parts of the space and start to learn. We had this co-occurrence matrix, and it gives a representation of words as co-occurrence vectors. And just one more note on that. I mean, there are actually two ways that people have commonly made these co-occurrence matrices. One corresponds to what we've seen already, that you use a window around a word, which is similar to word2vec, and that allows you to capture some locality and some of the syntactic and semantic proximity that's more fine-grained. The other way these co-occurrence matrices have often made is that normally documents have some structure, whether it's paragraphs or just actual web pages, size documents. So you can just make your window size a paragraph or a whole web page and count co-occurrence in those. And this is the kind of method that's often been used in information retrieval in methods like latent semantic analysis. Okay, so the question then is, are these kind of count word vectors good things to use? Well, people have used them. They're not terrible, but they have certain problems. The kind of problems that they have, well, firstly, they're huge, though very sparse. So this is back where I said before, if we had a vocabulary of 500,000 words, and then we have a 500,000 dimensional vector for each word, which is much, much bigger than the word vectors that we typically use. And it also means that because we have these very high dimensional vectors, that we have a lot of sparsity and a lot of randomness. So the results that you get tend to be noisier and less robust depending on what particular stuff was in the corpus. And so in general, people have found that you can get much better results by working with low dimensional vectors. So then the idea is we can store most of the important information about the distribution of words in the context of other words in a fixed small number of dimensions, giving a dense vector. And in practice, the dimensionality of the vectors that are used are normally somewhere between 25 and 1,000. And so at that point, we need to use some way to reduce the dimensionality of our count co-occurrence vectors. So if you have a good memory from a linear algebra class, you hopefully saw singular value decomposition, and it has various mathematical properties that I'm not going to talk about here of singular value projection, giving you an optimal way under a certain definition of optimality of producing a reduced dimensionality matrix that pair of matrices that maximally well lets you recover the original matrix. But the idea of the singular value decomposition is you can take any matrix, such as our count matrix, and you can decompose it into three matrices, U, a diagonal matrix sigma, and a V transpose matrix. And this works to any shape. Now, in these matrices, some parts of it are never used, because since this matrix is rectangular, there's nothing over here, and so this part of the V transpose matrix gets ignored. But if you're wanting to get smaller dimensional representations, what you do is take advantage of the fact that the singular values inside the diagonal sigma matrix are ordered from largest down to smallest. So what we can do is just delete out more of the matrix, delete out some singular values, which effectively means that in this product, some of U and some of V is also not used. And so then as a result of that, we're getting lower dimensional representations for our words if we're wanting to have word vectors, which still do as good as possible a job within the given dimensionality of enabling you to recover the original co-occurrence matrix. So from a linear algebra background, this is the obvious thing to use. So how does that work? Well, if you just build a raw count co-occurrence matrix and run SVD on that and try and use those as word vectors, it actually works poorly. And it works poorly because if you get into the mathematical assumptions of SVD, you're expecting to have these normally distributed errors, and what you're getting with word counts look not at all like some normal distributed, because you have exceedingly common words like after and you have a very large number of rare words. So that doesn't work very well. But you actually get something that works a lot better if you scale the counts in the cells. So to deal with this problem of extremely frequent words, there's some things we can do. We could just take the log of the raw counts. We could kind of cap the maximum count. We could throw away the function words. And any of these kind of ideas let you build, then have a co-occurrence matrix that you get